Oh, okay. Easy. All right. Hi, everyone. My name is Hayden Quinlan, and welcome to part two of our Getting Started with Additive Manufacturing webinar series. To the focus of today's session, we'll build upon what we spoke about last time. And if you weren't able to join us last time, I encourage you to watch the video recording. But the first part of our series focused on when and why to think about additive, where it makes sense, and how to sort of create a framework or a strategy for your organization to apply the technology. In today's webinar, we will now start where we left off. So we'll assume for a moment that we've made a commitment, we have a desire to deploy additive in our organization. And the focus of today's webinar will be on how we pick applications and how we pick processes and materials to support those applications for 3D printing. I'll do a little bit of recap to start, just again, in case you weren't part of the first webinar series. So first is just to remind you all where we are in the calendar year. This is a 6-part webinar series. The first one focused on getting started today on applications, as I mentioned. In the next webinar, we'll focus on applications from a different point of view. Today, we'll focus on technology and technical alignment. In the following session in June, we'll talk instead about economic alignment, how to make the money work and find applications of additive that can increase revenue or save cost. And then later on in the year, we have some more practical, or I shouldn't say more, they're all practical, but some very focused topics on equipment acquisition, sourcing strategies, how to set up facilities using additive, and then finally, how to stay in touch and how to make use of the outstanding resources that we have in New England that can help bolster you on your journey or skip some of the hard learnings and get you started more quickly. As a reminder of who we are, I'm the senior program manager here at MIT, and I've been teaching additive to professionals predominantly for the past 10 years. There's a lot more I could say about myself, but hopefully the fact that I know what I'm talking about will come out through the webinar. I will pass it over to my colleague, Dr. Mandana Moshiri, to introduce herself quickly.
Hi, I'm Mandana, but I just go by Mandy for short. I have a background as materials engineer, and I have a PhD in mechanical engineering. And for the past 10 years, I've been working on metal additive manufacturing. For 8 years, I've been focusing on the use of metal AM for molding and tooling applications, leading the R&D of metal AM materials and technologies for the Lega Group. And since July, I've joined MIT as a research scientist, where I work together with Hayden on the training programs and doing research on manufacturing technologies and cost models.
We're very, very happy to have you. That's the first time, man, you've introduced yourself and didn't say, I'm quite new to MIT. So, now I feel like you're really part of the family here.
Integrating.
Just a little bit about where we come from. We spent about 10 years, as I mentioned, teaching additive, beginning with workshops all the way back in 2015, building what was at the time the world's largest online course in 2018. And then over the last 4 or 5 years or so, what we've really been focused on are building laboratories and facilities to support not just MIT research, but industry end users who want to explore 3D printing technology. And I'll talk a little bit later on about how you can access those. And by a little bit later on, I mean on the very next slide. So just to say, if you are interested throughout this webinar series in printing some things, exploring technology, evaluating it, seeing if it makes sense for your organization, one of the themes of last webinar was that you do not need to commit, tens to hundreds of thousands of dollars of CapEx in order to start exploring additive technology. And one of the ways that you can explore that technology, if you're interested, is engaging with us at MIT and accessing some of our equipment, which is totally available to industry. That's the purpose why we built the facilities in the first place. So if you are interested in exploring 3D printing technology, whatever that means to you, getting a part printed, benchmarking a machine, asking us our opinion about it, whatever it is, you can feel free to reach out. And you can see, again, we have a full tool list here down on the bottom at the link on our website. So with that, that's enough of the promotional stuff or the logistics out of the way. I'm going to hand it over to Mandy, who will recap us for last month's webinar, and then get into the main sort of meat and potatoes of today's session.
Great, thank you, Hayden. So last time we actually talked a lot about the process change it takes for manufacturing parts using additive manufacturing, and we have discussed about that printing using additive manufacturing in your factory is not just pressing a print button and everything is done, but actually it requires many different steps. And we have also been discussing about we have been presenting this process chain that was focusing a little bit more on one of the most industrially used AM technology, which is laser powder fusion, in particular for metal, where you start designing your component. You need to upload it into a software. We can call it like a CAM software, but it's actually a job preparation software where you will orient the part, position it on the build plate, you will slice it, and you will convert it into a language that or into a format that the printer will understand. Then once it's uploaded on the printer, you will actually have to run some routine activities like uploading powder, like making sure the material is there, the gas is there, that the lasers are aligned and so on before actually pressing the button to print. And afterwards, there will be some immediate post process that involves the powdering, cleaning the pots, cutting from the build plate, heat treating, and depending on the part geometry, on the material you have been using, you might need to do some heat treatment before and after cutting. And then there will be all the final post-process and surface finishing steps, which should not be like ignored because they can be definitely not negligible. And these are all in order to reach the final dimensional tolerance and surface finishing that you expect from your part. And then we just put it in the end, but the quality control steps can happen at any point of the process chain, and these are essential to make sure that what you have manufactured can actually be used for your final application. If you move to the next slide, please. Can you? Thank you. So we also been talking, apart from the process chain, we also been talking about the main reasons why companies have been adopting additive manufacturing for their production. So these are the six main drivers that we have identified across industries. And one of the most famous reasons of adopting additive manufacturing is its ability to manufacture complex geometries. So components that have very complex structures like topology optimized lattice structures, all of it to achieve specific properties like bond growth, like also integration, but most commonly actually lightweighting. So having components that can satisfy the same type of mechanical performance but still be lighter. And similar to the complex geometries, but more on the internal side, like manufacturing parts with internal complex structures like cooling channels that can help improving performance, like for heat transfers, molding, and so on. Advanced material, you can actually print materials that would not be easy to manufacture with any other conventional technologies. And this is particular of interest, for example, for aerospace application. Mass customization, so manufacturing at extremely large volume parts which are single geometry, which are customized to the single patient. And one example here is actually Invisalign retainer. They are particularly famous for this type of employment. And then rapid fulfillment, we talk about producing spare parts, tooling, everything to keep your factory running, your production running. And last but not least, assembly consolidation. We'll actually have a slide about that where we talk about designing parts which are actually assembling multiple components. So in this way, you can have something which is easier to maintain, to manufacture, and also to control. If you go to the next slide, please. And we've wrapped up last time with the main three takeaways, which was to, first of all, to not underestimate the design. So when you design a part for additive manufacturing, or in general, actually for any manufacturing, inside the design of the part, you should not just think about the final application of the part or how you expect to perform it, but you should also consider how you want to manufacture it. So to make sure that the part you're designing, you can actually manufacture it, you can print it, you can post-process, you have access to the cutting tools you intend to use. So the design phase, during the design phase, you should involve as much as possible or as early as possible all the people which are expert of the different manufacturing steps of the process chain. The second takeaway was about thinking about the value addition. So we talked about the six main key performance drivers. So why you should print a part in AM, what is giving more or extra. So what is the value that is adding to your product. And this is something extremely important to make sure what you're manufacturing is actually can actually have a market space. And last but not least, we also talked about how it's important to that the AM journey can be very complex. You can do a lot of errors, and that would be completely normal. But the best way to learn it would be from someone else's errors. There are a lot of lessons learned around. You can reach out also to us. Hayden has actually shared a contact for the Center of Advanced Production Technologies, but also to service bureaus. Definitely, manufacturing with additive manufacturing is not just by purchasing a printer and start using it. There is a lot to learn here, and we'll actually touch upon this point a little bit more also during today's session. Can you move to, thank you. So now we will focus a little bit more about what makes a good application. And in here, we will touch upon again on the 6 main key drivers. So if you go to the next slide, thank you. So it's about asking ourselves when we should use additive manufacturing, where it makes sense. And if you go to the next slide, we can think about that our main focus should be the product, not the technology with which you manufacture the product. It's the product itself. A successful application will have a good combination of a technical fit and an economic fit. So we talk about not about if you should print something, but or let's frame it better. It's not, the question is not can you print something, because you can adjust the design in order to print pretty much everything, not like with the proper adjustments, but it's mainly about, should you print something, should you print a specific product, are you adding value by printing it? If you go to the next slide, thank you. So we can see additive manufacturing used at many different stages of the product life cycle. So we can see additive manufacturing being used during prototyping, concept design phase. And we have here examples like these potato chips, where the company was actually printing potato prototype in order to get feedbacks from the customer if it was feeling, if they like the feeling of the chips, before actually manufacturing all the tools that were required to produce a specific chip shape. But also in the end life, here we talk mainly about repair. Like here you can see the tram railways that were repaired, so in order to not have to replace the entire railway structures. We also talk about keeping a legacy vehicle on running when the vehicle is still working well, but you just need spare parts. Instead of keeping up the entire production line alive just for legacy vehicle, you can just print the spare parts that are needed. And the majority of application would be in the next slide. Thank you. Mainly about production. So today, additive manufacturing is not anymore such a new technology where we only talk about rapid prototyping. We can talk confidently about full production using additive manufacturing. And here you see a lot of different examples, like biomedical parts, like the acetabular hip replacement, the Invisalign retainer that we talked about, the Chanel brush, but also part of the airplanes, and we will touch upon some of these examples. So these are components that we can already see in our everyday life, which are actually printed. So they are they're full production. And if we go into the first phase, so concept generation and rapid prototyping, here we have very good examples from automotive industry. For example, Ford has actually shared it for their Explorer vehicle. They have actually used massively additive manufacturing for the prototyping stage. So it was mainly used from what you can see in the two pictures on the left, for some aesthetic evaluation, to making sure that everything that they were designing was actually satisfying the aesthetic standard that they had in mind. But also, as you can see in the last picture, the third picture, it was also used for doing crash tests. So when you run a crash test of an automotive vehicle, you actually need to use not only the same material, but also the same manufacturing method in order to do the test and for the test to be acceptable. So when some components were meant to be manufactured using plastic injection molding, it would have been too expensive to manufacture a steel mold just for a few dozens of components for the test, especially because we talk about rapid iteration here. So it was much more convenient to actually print in plastic the mold and then using this plastic mold for plastic injection molding and have the final part in the material and the manufacturing process that was meant for the crash test. So making it a successful application. Thank you. And then we move on to production application. So in production, of course, we can have a small, large scale of products. When we talk about small scale, a classic example is for tooling, so for plastic injection molding. In the example before from the automotive, we were talking about plastic soft tooling, but this would have been mainly for prototyping. Here we talk about tooling that are used for standard plastic injection molding, so steel tools. And the main reason why here it makes sense is because you can manufacture the tools with cooling channels, which are optimized for the shape. So if we go to the next slide. Thank you. You can actually see that if you want to manufacture a component using standard manufacturing technology, usually the cooling channel is just a straight line, which keep a sort of fixed distance from the mold cavity. But if you can print the parts, you can actually have a cooling channel which is following the shape of the conform of the cavity, making the cooling phase the cooling phase shorter, so you can reduce the cycle time, which can improve massively your productivity. Because as you can see from the graph on the right, the cooling phase during a plastic injection molding cycle time is actually the one that takes the most amount of time. So you can reduce this cycle time, but you can also manufacture mold parts which will look better because you can decrease the risk of warpage and distortion, especially if you have some thin walls and complex geometries. Can you move to the next slide? Thank you. And here an actual example, like where you can see with the colors, like this was a pressure washer housing that was molded, and you can see that on the example on the left where they use straight channels, there are parts which tend to be more red, so they have higher temperature. While if you have conformal cooling channels, so the cooling channels better follow the shape, the temperature is more in control on the overall geometry. Thank you. Um, Still about production examples, here we talk about medium to large scale manufacturing, and with a focus on the first key performance driver we talked about, so complex geometries and lightweighting. One of the best examples is probably the Riddell helmet. So this is a helmet used for football players, and it is printed in plastic using carbon 3D. And what they have been actually optimizing here is that the entire helmet is printed using lattice structure, where the unit cell geometry change depending on the area of the helmet. So Riddell has collected a lot of data in the past, knowing which areas of the helmet require which is subjected to which type of heat and require which type of protections. So basically they optimize the unit cell geometry to have, for example, in some areas a higher resistance, in other area they prioritize, for example, comfort and lightweighting. So this entire helmet is actually customized to the specific head of the player in order to have best protection and performance. And the results is actually proving it. So it was actually reaching. It was actually the best performing helmet from the laboratory test for the NFL. Thank you. Oh, can you click again, please? Thank you. Another example of production scale, of large production scale AM parts is actually a quite new application. It's actually been released last year, where Apple officially shared that they have been printing the cases for the watch using laser powered fusion metal AM. And this actually gave the opportunity to have to use recycled titanium powder, the use of this technology was actually helping Apple to get closer to their sustainability goal for 2030. But at the same time, they were exploiting the possibility to have specific texture in certain areas of the case in order to have, for example, higher waterproofing performance. So overall, AM was here helping having a higher functionality and sustainability and achieve their sustainability goal. Thank you. Still about production, here we focus a little bit more on spare parts, and probably one of the best example is given by Deutsche Bahn, which is the German railways company, where they have been using massively additive manufacturing, both of metal and plastic, for manufacturing on demand of spare parts in order to decrease more and more the warehouse where basically now they just have a digital warehouse. So when a component on a train it's broken, the person will just log in on a digital warehouse, place the order, the part is going to be printed and shipped where it's needed. And since 2015, Deutsche Bahn actually claims that they have saved more than 20 million euros across the year. We are talking about more than $23 million. And they have been using it for over 200,000 spare parts. And this has actually helped them getting the trains back on track faster and improving the reliability of the rail infrastructure. If you can go to the next slide. Thank you. Here we have some examples on where it has been used. So it was used both on smaller components, like here we can see on the two pictures in the left that there was just printing in plastic some frame to help placing the labels on the train seats, but also larger parts, like for example this metal component on the train. It actually broke in service. So what they did was to, sorry, can you go here? They actually took the broken part, they 3D scan it, they reverse engineer it, and then they printed the components, and they actually saved the design on their digital warehouse. So if this happens again, they can just place an order to reprint it. And on the last picture, this is also another very nice application, which is they have been printing these handrail signals with Braille. So to actually help blind people to find their way in German train stations, so to help the mobility for everyone. And now we can change slides. Thank you. But I love these slides. It's probably one of my favorite application because it's about assembly consolidation. So GE Aerospace is probably it's one of the champion in showing very interesting part where they have been assembling components. So for the catalyst to turboprop engine, which is used for civil aviation engine, we can see that this entire engine was made conventionally of 855 parts. And thanks to assembling the design for additive manufacturing, it was reduced down to 12. So this means 30% of the components actually was printed. It was lighter. There was better fuel consumption. But when we talk about 855 parts down to 12, it's not just the fact that the engine will be lighter. We also talk about saving warehouse space, saving purchase cost, paperwork, all the maintenance and the assembly time and the risk of errors which are involved when you handle more than 800 components instead of handling just 12. And overall, it's also helping the maintenance because this engine, every X amount of fly hour, they will need to be controlled for safety. Now the safety just need to be done on 12 parts instead of 855, making the entire engine also more reliable. So there are massive benefits when we talk about assembly consolidation. Thank you. And last but not least, we also talk about end life. When we mentioned very quickly about legacy vehicle, and one example is actually coming from Porsche, where it had this legacy car, and they only produced only a specific number of these cars, but to keep them, to make sure that they could actually manufacture spare parts for the people who purchase it, they are actually employing additive manufacturing just to print the parts on demand when it's needed. And there is another very interesting example of end of life in the next slide, but I'll give the word to Hayden since you're also in the picture.
Thank you, Mandy. Sort of the last application we want to highlight here on the sort of recap or the exploration of why you would use additive and for what purpose for uh, spot repair. So additive technologies are fairly flexible in the sense that we can exchange a build plate for, in this case, a steel beam, and instead of having the equipment here in the lab, we can bring it out to the field and directly print material in place. So this application is a civil infrastructure application. The idea is that we can restore corroded capacity to damaged steel by, in this case, it's not welding, but you can almost think about it as sort of filling in the gaps using an additive process called cold spray. And all of the previous slides were kind of meant to give you an overview of why do people choose to use additive? What are the types of applications that make sense for the technology and that match to, if you remember way back at the beginning of the deck, when he mentions technical and economic fit, right? Many of these applications here are meeting both criteria. But especially a lot of the value drivers that we're talking about can be expressed in both terms, but there's always sort of strong technical alignment. And so in the next portion of the webinar, we want to give you some tools to assess that technical alignment. And if I put myself in your shoes, right, you can look at those previous applications from a few different lenses. One is maybe you're an OEM yourself. You make products that you then sell. In that case, a lot of the value that we talked about previously comes from a design point of view. How can you incorporate, right, the design flexibility of additive into your products to build better products, whether they're better performing or they're easier to service, as Mandy was talking about, or whatever other benefits you might tap into that we talked about previously. You can also think about this as from a capabilities point of view, which is maybe you're a supplier, but you're not someone who's making parts yourself. And you're thinking about what kind of capabilities should my shop have based on the industries that I'm serving, and how can I sort of go and win more business by being able to offer more capabilities than just, CNC machining or grinding or injection molding or whatever it is that you currently offer. And the way that we like to encourage you to think about it, right, is to like pick the right material and process. And ultimately, what that comes down to often is understanding the iterative loop in additive manufacturing. Is that we will design things to be printed, we will go and print them, and then we will test to see how good of a job that we did. And so you might be familiar with your machine tools, and every part you ever make is perfectly in spec. Nothing ever goes wrong, right? Like you're a master of your CAM programming or whatever it is. The bad news in additive is that there are very few people or very few machines in the world where you'll get everything perfect on that first shot. And so a lot of the 3D printing process is about printing something, testing it, meaning dimensional inspection or material or mechanical characterization, depends on what your application cares about, and then iterating and changing something in your design or in your process workflow. And so what we want to talk about in the following slides is how do you make that loop as small as possible? How do you streamline the process such that you can exit this loop and go from design, print, sell, or design, print, deploy, or whatever action word we want to use, rather than constantly kind of spinning around and testing things and pulling your hair out and saying what's going wrong, I can't figure it out. So where that starts is picking the right 3D printing process for your end application or for the capabilities that you want. And I would encourage you not to think about this as I want to print polymers or I want to print metals. Because if you think about things in that terms, you have way more options in front of you. There are many machines that can print polymers and many different machines that can print metals. Instead, what you want to think about, and it's a little bit hard to see with the resolution, but you want to think about these bottom rows here where it says strengths and typical materials, which is what is this process good at? What is it not that good at? And how does that map to my desired outcome? And I can give you some really simple examples, which is, say, for example, material extrusion. Let me turn on my laser pointer. So in material extrusion, when most people think 3D printer, this is what they think of, like the desktop machine squeezing out plastic, and printing small thermoplastic parts. And those machines are great. They're low cost, they're super easy to use. They use materials that we're all familiar with, like ABS, for example. But at the same time, they have a lot of limitations in dimensional accuracy and the strength of the parts that you produce, etc. And so, if we think about tooling applications, and many of the examples that Mandy showed previously, like from Deutsche Bahn and others, where they have alignment jigs and fixtures and things like that, those are printed on extrusion machines because the part doesn't need to be perfectly strong. It's simply an alignment fixture. It's going to bear no load whatsoever, and I just want a tool that I can make quickly and inexpensively, and deliver to the field. Conversely, when we look at, for example, those football helmets that Mandy talked about, we would never use material extrusion for an application like that, and that requires a little bit of process understanding. But it's because the strength of the material is not isotropic, meaning it's not of equal strength in all directions, but it's a little bit weak where the layers overlap with one another. So instead, the process that they use is the one all the way on the left, that photopolymerization, because that can make fully cross-linked elastomeric polymer components, meaning that they have fairly isotropic mechanical properties, and we can use them in applications where, for example, if you're playing football, you're taking hits in all different directions, and we want to keep you protected in all different directions. And so, this is a bit of an older slide, but there are many, we're going to go through many different sort of process comparison examples. A lot of the way that you then want to think about the technology is like, what's going to give me the right capability space for the applications and the demand that I know I have. So what can I put to use where the things I'm going to make, I'll be able to sell. That's number one. But number two is, how do I match those capabilities to my targets? And my target might be production targets, in which case we care about the y-axis. We care about build rate. That's really, really important for us. And some processes are a lot faster than others. As you can see, there's kind of extremes here. We might also care about resolution if I'm making really finely detailed parts versus, really big, kind of not so sensitive to tolerance components. So then we care about the bottom. The x-axis, this is expressed as layer thickness, but you can also sort of treat layer thickness as a proxy for resolution. Layer thickness would be the resolution of the z-axis, and then there'd be like xy as well. But they're usually roughly the same. And so depending on what it is that you want to do, right, you might pick certain machine capabilities in this space, and those could be driven again by the technical objectives of your application. But of equal importance, and something we'll get into a lot in following webinars, is the economics and what makes sense for you to really deploy. And not to wax too poetic on the economics, but if you recall, last webinar, what Mandy kind of kicked us off with about how additive is just one box in that long process chain. You don't just want to think about the build rate or layer thickness for your printer, but you want to think about, in order to hit the target that I have, can I get that target off of the machine, off the printer itself? And often the answer is no. And you have to say, well, what other steps do I need to think about as part of my value chain in order to hit those targets? And then you can really get a sort of good complete picture of what's necessary to use additive for what you intend to use it for. And again, just another process comparison of metals. You'll find many of these online. You'll also find many different competitive acronyms, so like LWDED and AWDED and EBWDED and so on. There are always different acronyms in the additive world. And some of these, I'm like, the only time I've ever seen AWDED is on this slide. But just to say, actually, I think I'm just trying to say it can be a little bit complicated, and the landscape is really pretty intense. And there are many different types of machine manufacturers, or types of, in this case, the acronym before the DED refers to the energy source, or the feedstock material. So electron beam, and maybe the W is wire, and LW is laser wire, and so on. And so what you realize is, if you're buying how do I say this? Like, you don't want to think about buying a 3D printer in the same way that you think about buying a vacuum cleaner for your home or a microwave or some other general appliance, where you're looking at, oh, what does it cost relative to this other machine and how big is it and so on. You want to use the same amount of specificity that you would use if you were selecting any other machine tool in your shop. And that means evaluating, the energy source, evaluating the cost of the machine, evaluating the parameters that these are compared on, build rate and resolution, and many other things will influence that decision. And it's kind of hard for us to say this in generic terms on a webinar, which is why I'm being a little bit sort of dancing around it. But I'll say it depends really on what it is you're trying to do. And you see the parts that are shown here, there's no scale bar, but some of these parts are huge and some of them are actually really small. And that also makes a big difference. So the part that you see with my red annotation, I have that part in my office. So that fits in the palm of your hand. If we go over here to this like thruster component, right, this is probably a pretty massive part, something that like, would be a lot of effort to lift up with two arms. And so you always just kind of want to think about machine capability again in the context of what it is you're trying to do. And if we look at different polymer additive processes as one way to compare, we can almost immediately from looking at the parts begin to compare and contrast what makes some processes more suitable for some applications and other processes suitable for others. So in FFF for material extrusion, this is again the standard printing process, we can make thermoplastic products and they look pretty good, but they don't look perfect. Even in this picture, you can see layer lines and so on. So this is good for low cost, sort of quick and dirty applications, applications where we don't care that much about strength or we don't care that much about aesthetic finish. On the right, to the right of this, we have that photopolymerization, that clear part. And in that case, it might be a little bit hard to tell, but generally has much better surface resolution, surface texture than an FFF part because the layer lines are not as pronounced, although actually you can see them in this part, which is sort of interesting. It's not always the case for a photopolymerization print. We also see a clear material, which is traditionally difficult to do in thermoplastics extrusion, especially because the layer lines create problems, even if your material is totally transparent. But in the case of if you want clear components, now maybe not optically clear, which has like a special meaning, but generally clear to the layman, then photopolymerization can be a great option. But we also see a lot of support material. And depending on what it is you're printing, removing that support material, A, can add a lot of time. But B, and more importantly, it sort of competes with some of the advantages of photopolymerization in the sense that it will leave a residual mark on the part after you break away that support material. So you'll have to sort of sand that down or otherwise remove it. And depending on what it is you want to accomplish, right, that could be too much time, too much of a hassle for you. To the right, we have a bit of a flex of a print, to be honest. This is material jettings, what the MJ stands for, from a company called Memaki. And they can make full color models and print mixed colored materials. Not mixed materials. Some machines can do that. The Memaki printers cannot, but they can print full color. And so, and also the support, this model wouldn't have needed support because it's just sort of a column, but the support is really easy to remove. So if I care about model making applications, if I really care about aesthetic quality, but I don't care at all about strength, and I don't care at all what material it is, I just want to make something beautiful, material jetting might be the right process. And then last, we have powder bed fusion on the right, maybe from Form Labs, and I'm just guessing based on the color of the part. I could be totally wrong about that. No, I'm looking at the link at the bottom. I am totally wrong about that. It's from a Kickstarter campaign. But that uses a powder material that's fused with a laser. And what that means is that it can be really fast. It can use really low cost materials like chopped nylon feedstock and so on. It tends to be a lot faster than any of those other processes I mentioned. But at the same time, because we're using powder, you see that surface finish is really coarse and rough. And that's very typical of parts made by powder bed fusion. So if I care a lot about surface finish, that might not be the best process for me. And there are many more, like we could get into the weeds here. I'm probably spending too much time already on this slide, but I just want to say when you think about your end application, it tends to make sense to like list all these things out. What makes this process good? Where does this process kind of struggle against others and start to rank? What do you really care about for what it is that you're selling or what capability you want to have? Because you don't want to sort of make speculative investments. You don't want to see this Mamaki part and be like, man, that's beautiful. I would love to have one of those machines. Now, granted, that happened to me, and it's been a really useful machine for us at MIT. But for you, it might not be the case. So you really want to match these capabilities for what it is you're trying to accomplish. And then last, right, like understand that the material, or sorry, that the outcomes that you get are not just process dependent, but they are material dependent as well. And because the material formulation might be slightly different even if the end part is the same, if it's still aluminum oxide or if it's still silicon carbide, really common printed ceramic material, the way that you get to that product, the way that you get to that material might require you to tweak it in some way to suspend. In the case of ceramic, it's often like suspending the ceramic inside of some other, thermoplastic or UV curable resin that will change the outcome that you get, even if the end material is the same. And so you can see differences between binder jet parts, which again, that's sort of a powder based process. So you see that rough surface finish between photopolymerization and material jet parts, which are really gorgeous and like have really nice surface finish as a result of the process. But there's some other intricacies we could get into there that make it a little bit complicated, like your machine gets really messy, for example. And then on the right, we have extrusion, where, like, with all due respect to extrusion technology, like the cube you see on the right, that's half ceramic, half polymer, that looks horrible. So it sort of depends, like for an R&D purpose or for playing with mixed materials, maybe that makes sense. But for end use parts, right, maybe it doesn't make a whole lot of sense. And now I'm going to pass it back over to Mandy, who's going to talk a little bit about how do you pick machines and compare equipment against one another for the purpose of seeking those winning applications.
Thank you, Hayden. So, connecting to what Hayden has been saying in the previous slides, there are many different machines, there are many different technologies. How do you select the best one for what you want to do? And especially in the past, there has been like a rich literature about machines and process benchmark. This benchmark sample is particularly famous. This is from the National Institute of Standard and Technologies, where you can see many different features that were designed in order to evaluate the process capability. So you can see that there are holes, stairs, like all these circles, and also to evaluate the flatness capabilities. This this benchmark itself has been used mainly to compare different processes. So as you could see in the previous slides, with all the different manufacturing processes, and you could see maybe the best example was the slide with the little boat. This design in particular was done to evaluate the design capabilities using something that could be easier correlated to your components rather than the boat. If you move to the next slide, please. Yeah, thank you. But the design itself, like the previous one from NIST, makes sense if you can recognize these features actually reliable, like not relatable to your application. There has been also other type of benchmark developed in literature. So, for example, there has been this spiral sample that was designed for being applied for molding companies, where the spiral channel is actually going to resemble conformal cooling channels. And there are all features like overhangs, small holes, thin walls, everything that you can find. Everything that you can find on a mold design, on a mold part. And this specific benchmark was not done to compare different processes. The process that was meant to be used for molding was very clear. That was metal laser powder bed fusion. This specific benchmark was designed to resemble an application and to compare different suppliers. So what you see here, the letter A to H were different suppliers. And letter E was not forgotten. It was just a supplier that didn't manage to print the geometry, to print the benchmark job. And the 1, 2, 3 is actually the different jobs. So in this benchmark, also the repeatability of the machine was being evaluated. So how much a machine can print 3 times the same parts and how similar will be these parts, because of course there is always a little bit of variability. And what we see here are the 3D scan of the specific geometry. And if you're not familiar in reading a 3D scan contour plot, it's very simple. The greener, the better. So the greener it is, the closest it is to the nominal design, to the CAD design. The more colorful it gets, the more you're far from a nominal design, so the more distorted the part is. And we can see that some companies did pretty well in terms of repeatability. So if we look at company C, across the 3 jobs, the parts are basically identical, which is actually not so common, especially if you look at everything else. But they were not accurate at all. Like you can see how black it was here. So they were very much distorted from the original geometry. If we look at other companies like the company F, we can see that the pods were pretty accurate. They were very green, especially the 3rd job was almost perfect, but they were not very repeatable. And then there was company H, which was pretty good in terms of repeatability and in terms of accuracy. And one important thing that came out through this research was that company H was actually using a machine which was approximately 10 years older than all the other companies. And this is so important to remember that the technician and the know-how, the user knowledge can really play a difference in this complex machinery. So this is something you get to know the more you use the printer. And this is also why throughout all these webinars, we are highlighting how important it is to reach out to your network, reach out to service bureaus, reaching out to people who has been using this equipment for years to get all this tacit knowledge, this know-how. If you go to the next slide, please. So if we move on from just the process and now we talk a bit more again about materials, and we are trying, and here is just pretty much a repetition to what Hayden already said about materials and process. Like you can have in mind a specific material, a specific process you want to use. Not all material can be used for every process. So there is this matrix. This matrix is also a little bit outdated. If you want to use in general, since the technology is developing every day, if you have a specific material in mind or a specific process you want to use, the best way would be to reach out to manufacturers, service bureaus, and see what is actually available. But you can see that some processes are particularly strong in processing specific materials in dedicated feedstock. This is also something important to consider if it's a wire, if it's a powder, if it's a liquid. Also because depending on the feedstock, also the health and safety requirements for your facility will change. For example, if you use a wire, a metal wire as a feedstock, the level of safety in your facility is definitely lower if you, for example, use metal powder. So also the ease of use will change greatly here. If you go to the next slide, thank you. So one thing that it's also very important to remember, and this graph is pretty complex. It looks like a lot of spaghetti being entangled, but there is one concept here that we want to share from this slide, and this is that the material properties, the properties of your final part, will not only depend on the material you choose, but will also depend on how you process the part. So if you print a specific steel, the type of printing parameters you use, the type of post-process you will use, so the type of heat treatment, the type of surface finishing that you will employ, will affect the final properties. And this is very much so important to keep in mind, and that that these final properties will be affected by the entire history of the component. And this is also something that suppliers are very well aware, and we can show it in the next slide. An example. Yes, thank you. So this supplier is actually EOS, is one of the biggest AM printer suppliers in the world. And what you see here is actually taken from their material data sheets. So you see that they sell 316L powder. And in their material data sheets, you can actually find these graphs where they're comparing, they're showing the as-built tensile properties that you can get when you print this material with two different machines still of their machine park or different printing parameters. So here they're just printing standard stainless steel 316L. They're testing it in as-built condition, and very important is that with additive manufacturing, properties are anisotropic, so they will be different depending if you print, like if you measure it in which direction. So what you see here is that it's a bit small, but you will see that for every property tested, the measurements are in the vertical or horizontal direction, and you can see that they can be greatly different. But then you can also see that if you use EOS M290 or EOS M404, these are two different type of printers that EOS sell, or if you use 20 micron or 40 microns printing parameter sets, the properties greatly change. So if we just take the yield strength, which is the first one, we can see that not just the average of the yield strength change depending on the printer, depending on the printing parameters, but also the standard deviation changes. This can be extremely relevant, especially if you work with pods that require certifications. So it's very important to consider. And in here, they just measure the as-built conditions. Of course, it should be the situation. The numbers will be even again different after heat treating, after doing all the subsequent post process. So it's something extremely important to consider when you evaluate which material you want to use. You need also to think how you're going to process this, with which parameter you're going to print it, and how you will going to handle the entire manufacturing chain. If you could, thank you. One thing you can do in order to help you the down selections of different processes, because it can be quite overwhelming. We talked about it. There are many different materials, many different processes. Like, how can you handle all of that? And you can handle it just by starting with what you know best, which is your application, which is your product. So you start with your product, then you try to be as thorough as possible, defining which requirement your product needs to satisfy. We're talking about dimensional requirement, which mechanical, electrical, chemical properties are expected from this product in service, what type of finishing surfaces you need, what's the cost target. So as thorough, as detailed as possible, you can write down the requirement list. And based on that, you just follow like a sort of funnel type of strategy. So along all the material classes, which one makes most sense for this type of requirements? Are we talking about metal? Are we talking about polymers, ceramics, composites? Not about a specific alloy. We're just thinking like in general terms at this phase. And then based on the material class, you can start identifying the technology family, because as Hayden was showing, depending on the technology family you use, you can prioritize mechanical properties, you can prioritize aesthetic, you can prioritize uh, fast or cheap printing. So there are different areas that you can prioritize. And once you have this overview, you can actually build a decision process chart where in each row you write your requirements. And in the column, you write the different options which is a combination of material and technology. And then one by one, you see if this requirement would be satisfied for each options. And you can decide just to write V and X. You can decide to give a grade. You can also decide that one of the options you want to put in the comparison is the current method you're using to manufacture your product. In this way, you have a very good comparison on what is the value I'm potentially adding, if I'm adding any. And if I'm not adding any value by using a new technology or a new material, maybe it doesn't make sense to print it. Maybe I should change something else in my evaluation. So building this concept chart will not giving you an answer. It will just give you probably two, three options. And then with these two, three options, you can reach out and actually go to service bureaus in your network and maybe ask for printed parts in order to actually do some tests and evaluation on the printed part itself. Go to the next slide. Thank you. And as usual, we want to wrap up with the main three takeaways. So it was a long presentation, so a long webinar. So the main three takeaways we would like you to remember is that, first of all, it's very important that you know your application and you ask yourself, should I print it? Not can I print it, but does it make sense to print it? Then you cannot escape the iterative nature of additive manufacturing. So you design, you print, you test, you iterate. So you can run tests, you can run benchmark to find the best technology. And third, starting from your product requirements, you can down select your options using something like this concept chart in order to help you identifying the best options to then to further test on.
Yeah, thank you, Mandy. I'm going to skip some of this stuff at the end. So we have 3 minutes, and if anyone stayed for the full thing, thank you. And actually, I want to just add a couple of very specific pieces of advice to what Mandy shared previously. So first on this benchmarking thing. If you plan to buy equipment or plan to buy parts from an additive supplier, you should demand that they produce benchmark components for you. And if they're really capable and your parts aren't really hard to make, they should do that at no or low cost. If they're really hard to make, you might have to pay for it, to be honest. But you should always demand this up front, and do the scanning and everything yourself. And then the second question you should ask if you're buying parts, not machines, but parts specifically, is after you get a benchmark that you're happy with, right? Ask them, hey, who's printing these parts for my production run? Is it the same person in the same machine that made this really good benchmark? And if the answer is no, because sometimes the answer is no, right? You might want to re-benchmark based on the actual production partner. But there's a little bit of like sort of important detail there where you see the differences in one, two, and three, right? Same exact part, same exact process, but slightly different outcomes. And that could be different material, different machine, etc. And you want to try to isolate that as much as possible. And remember, as the buyer, you have the power to kind of push them around a little bit and make sure that you're getting what you want before you commit to what you buy. That's the first thing I wanted to say. The second, um, is on this chart in particular. So this is going to be some specificity to laser powder bed fusion for a second. But the important thing you should take away from this, in addition to what Mandy said, is just that there's a lot of variation. And so if you are planning to sell parts into regulated industries like medical devices, aerospace, defense, etc., granted, you already need to have a good quality management system. You probably already know about ISO 9001 or AS 9100D or et cetera. But I just want to say your QMS becomes a lot even more important, because you have this intrinsic variation in process outcomes depending on how you approach, the printing process. And so it's really important that you pay attention to quality management. And if you're thinking about, right, hey, this is a lot of stuff for me to control. How do I reduce as much variation as possible? What standards exist out there? We will say there are really robust ASTM standards, and there are also many standards from the Society for Aerospace Engineers, SAE, and a lot of the ASTM standards pull on those SAE standards. So I would also encourage you to like look through those documents. And granted, sometimes they're like $100 each, so it's a little annoying to buy them. But because that'll also inform, if we like reflect back on what Mandy started with, what are all the other machines and processes I'll need in order to hit those target material properties. And then the last thing I'll say, and sorry, I'm going on, but is really important from a machine selection point of view, is why are the first two printers, why do they have more variation than the last printer that's shown? And one reason could be because they're earlier generation machines. So they've probably figured some tricks out with respect to gas flow and other things like thermal insulation in the build, et cetera. But number two is you see the Dash 4 next to the M400. And that's a four laser machine versus a single laser machine. And there's like a lot of nuance, and I'm not going to get into it, but basically how the laser strikes the powder bed and what that spot looks like affects your mechanical properties. And having more lasers so you can control their positioning a little bit better because they don't have to cover the full build volume, that affects the outcomes that you get. And that might be, I don't know for sure, but that might be one reason why we get a tighter, distribution of mechanical performance. So the point I'm trying to make by like rattling off all these details, I don't expect you to memorize them. It's just to say that every little thing matters from a component selection, from a process selection point of view. And that's why at the very beginning, and I'll like jump back through these 100 slides just to recap